As we said, pages are the more popular method for memory management. Now, let's take a look at one of the major components that enables page-based memory management, and that's page tables. That's the component that's used to translate the virtual memory addresses into physical memory addresses. So here is a page table. For each virtual address, an entry in the page table is used to determine the actual physical location that corresponds to that virtual address. So in this way, the page table is like a map that tells the operating system and the hardware itself where to find specific virtual memory references. Although the sizes in this drawing are a little bit off, the sizes of the pages of the virtual memory and the corresponding page frames in physical memory are identical. By keeping the size of these two the same, we don't have to keep track of the translation of every single individual virtual address. Instead, we can only translate the first virtual address in a page to the first virtual address in a page frame in physical memory, and then the remaining addresses in the virtual memory page will map to the corresponding offsets in the physical memory page frame. As a result, we can reduce the number of entries we have to maintain in the page table. What that means is that only the first portion of the virtual address is used to index into the page table. We call this part of the virtual address the virtual page number, and the rest of the virtual address is the actual offset. The virtual page number is used as an offset into the page table, and that will produce the physical frame number, and that is the physical address of the physical frame in DRAM. Now, to complete the full translation of the virtual address, that physical frame number needs to be summed with the offset that's specified in the later part of the virtual address to produce the actual virtual address. That resulting physical address can ultimately be used to reference the appropriate location in physical memory. Let's look at an example now. Let's say we want to access some data structure, some array, for instance, to initialize it for the very first time. However, we have already allocated the memory for that array into the virtual address space of the process, but we've just never accessed it before. So since this portion of the address space has not been accessed before, the OS has not yet allocated memory for it. What will happen the first time we access this memory is that the operating system will realize that there isn't physical memory that corresponds to this range of virtual memory addresses. So it will take a page of physical memory, P2 in this case, the page that is free, obviously, and it will establish a mapping between this virtual address, so this is the VK and the offset address where the array is placed in virtual memory, and the physical address of page 2 in physical memory. Note that I said that the physical memory for this array is only allocated when the process is first trying to access it during this initialization routine. We refer to this as allocation on first touch. The reason for this is that we want to make sure that physical memory is allocated only when it's really needed, because sometimes programmers may create data structures that they don't really use. If a process hasn't used some of its memory pages for a long time, it is likely that those pages will be reclaimed. So the contents will no longer be present in physical memory. They will be reclaimed, they will be pushed on disk, and probably some other content will find its way into the physical memory. In order to detect this, page table entries don't just consist of the physical frame number. Instead, they also have a number of bits that tell the memory management system something about the validity of the access. For instance, if the page is in memory and the mapping is valid, then this bit is 1. If the page is not in memory, then this bit is 0. And if the hardware MMU sees that this is a bit 0 in the page table entry, it will raise a fault. It will trap to the operating system. If the hardware determines that the mapping is invalid and false, then control gets passed to the operating system. The OS at that point gets to decide a number of questions. Should the access be permitted? Where exactly is the page located? Where should it be brought into DRAM? As long as a valid address is being accessed, ultimately, on fault, there will be a mapping that will be reestablished between a valid virtual address and a valid location in physical memory. It is likely, however, if the page was pushed on disk and now is being brought back into memory, that it will be placed in a completely different memory location. So for instance, here, this page is now placed in P3 and it used to be in P2. As a result, clearly the entry in the page table needs to be correctly updated. So as a final note, to summarize, the operating system creates a page table for every process that it runs. As a summary, the operating system will maintain a page table on every single process that exists. That means that whenever a context switch is performed, the operating system has to make sure that it switches to the page table of the newly context switched process. We said that hardware assists with page table accesses by maintaining a register that points to the active page table. On x86 platforms, there's a register CR3, and so basically on a context switch, we will have to change the contents of the CR3 register with the address of the new page table.